I would now like to invite Assistant Professor Leong, Deputy Director of CLIC, to present her talk.
Hi, I'm Victoria, a Deputy Director of CLIC, and today I'd like to tell you about becoming mentally flexible. Mental flexibility is a foundational life skill. In our everyday lives, it helps us to be creative, to take someone else's perspective, to correct our responses after we make a mistake, to shift our focus between different tasks, and perhaps most of all, in today's volatile climate, it helps us to manage change or uncertainty when things don't go to plan, when plans change, or when we simply cannot make long-term plans at all. People who are resilient tend to be flexible in the way that they think about challenges, but also flexible in their responses. So how do we build flexibility from an early age? Cognitive flexibility emerges gradually during the early childhood years of 0 to 6, alongside other executive functioning skills like working memory and inhibition. But precursors of flexibility can already be measured during infancy, such as overcoming perseveration and reversal learning. This protracted window of development gives us an opportunity to foster flexibility. But we still don't know everything about the neurodevelopmental mechanisms that underpin the emergence of flexible thinking. In adults, the functional organization of brain network activity changes dynamically over time. So this means that a particular brain region can change its allegiance from one functional module to another depending on the circumstances. And this is called neural network flexibility. And it's known to contribute toward cognitive flexibility and learning. For example, when adults do a motor learning task, their neural flexibility in one session predicts success of learning in a future session. In this study with infants, Yin and colleagues studied the development of neural flexibility in a cohort of 52 healthy infants whom they scanned longitudinally 7 times over the period of 0 to 2 years. Their results dramatically illustrated that there were changes in neural flexibility across many brain regions, but most importantly, in the regions that support flexible thinking, such as the anterior cingulate cortex and insula, the inferior frontal gyrus, the temporoparietal junction, and the posterior parietal cortex. Data like this tells us that flexible behavior is likely to require a flexible brain. So how do we build a flexible brain? Well, early brain development is experience dependent. Experience builds brain architecture during the early sensitive periods when the neuroplasticity of the brain is high. Most of the child's early life experiences involve social interactions with adults who have an important role to play in scaffolding early learning. So if we invest in building a flexible brain during infancy, this could lay the foundation for a lifetime of flexible thinking. But what types of experiences are best at stimulating early neural flexibility? In CLIC, we're starting with a skill that babies are already very good at. Although their executive skills are still maturing, babies excel at finding patterns. For example, in this classic statistical learning task, even 6-month-old babies can already track the transitional probabilities between syllables in a seemingly random syllable stream. And they can use these statistics to infer word boundaries and to segment speech. So babies are good at statistical learning, but they're bad at flexibility. And in fact, it's quite hard to measure flexibility at this age. So we have to think of clever ways to infer this based on babies' behavior. For example, in this sequential touching object categorization task, we are offering Max a choice of 8 different objects, 4 balls and 4 cubes. But Max only plays with the balls and he avoids the cubes. His sequence of touching the objects tells us that he has mentally separated the 8 objects into 2 categories based on their shape. So next, we will demonstrate to Max that 2 of the balls are made of a soft compressible material, whereas 2 of the balls are hard and unyielding. And the same is true for the cubes. After this demonstration, will Max be able to change and recategorize the objects based on whether they are soft or hard? Well, you have to come into our lab to find out. So in CLIC, we are leveraging on babies' good statistical learning skills as a springboard to improving flexibility. And our structured learning program is specially designed to train babies to stay open and alert to changes and new statistics in their environment, and not to get locked in to just one way of responding. I want to talk to you about another exciting CLIC project. Our cortical neural oscillations have an important functional role in entraining to and parsing temporal structure in our environment, such as the syllable stream you saw earlier. Stimuli that arrive in the brain during a high excitability oscillation phase are more likely to be encoded than stimuli that arrive at a low excitability phase. Further, although our brains generate oscillations across a range of frequencies, we each have peak oscillation rates that are different and that reflect our personal preferred rates of information processing. So can we optimize learning by matching the timing of sensory input to our personal oscillation rates and by targeting the optimal phase? Well, we've already started to collect data and the results are promising. As you can see here, when stimuli were arriving at the matched personal alpha rate for the individuals and at the right phase, then the adult's learning rate was significantly better than when the stimuli were arriving at the wrong rate or at the wrong phase. Finally, I want to talk about barriers to flexibility. In adults, stress increases rigid, habitual, ineffective response strategies at the cost of being flexible. The same is true of infants. In this study, Seehagen and colleagues exposed a group of babies to a mild stressor, separation from their parents temporarily, and a second group of control babies were not separated or stressed. Both groups of babies were then given an instrumental learning task where they had to learn to activate this light switch by pressing on a button. They were then allowed to press the button as much as they liked until they habituated, and then the experimenters deactivated the switch so that pressing it no longer turned on the light. And they were interested in whether babies would continue to make futile button pressing responses. As you can see in their results, babies who experienced stress made more perseverative, ineffective button presses over a longer period of time. By contrast, babies who were not stressed very quickly learned the change in the rule and switched their response strategy. A second important factor is mental health, which is a growing global concern. Mood disorders like depression and anxiety affect 1 in 5 of us, and these disorders are associated with impaired shifting and flexible adaptation of goal-directed behavior, which seems to be implicated in the causal etiology and also to predict symptom severity. This means that if we address mental health issues, we could indirectly improve flexibility. Conversely, if we build flexibility, this could confer resilience to future mental health issues. Let me leave you with 4 take-home messages. To develop flexible behavior, we need to build a flexible brain. And the early years may be the best time for nurturing flexibility, given the protracted EF development and high ambient neuroplasticity. And there's vast potential for personalizing learning in the future based on neural characteristics. But we cannot build flexibility without first removing barriers like stress and mental health problems. If you found this topic interesting and you want to test your own flexibility skills, our PhD student Lena has made a great little demo that you can try from the comfort of your own home. Now, this works in a web browser, so all you have to do is type in this web link or scan this QR code, which will bring you to this web page where there are further instructions. Well, I very much hope that you've enjoyed this talk and that you will continue to follow CLIC's work in the future as we get our program off the ground. Thank you very much for your attention.
Thank you very much, Assistant Professor Leong. It is my pleasure to invite Professor Hang, Dean of the Education Research at the National Institute of Education, to give his speech.
Good evening. I'm David from the National Institute of Education, NTU, and I'm honored to be part of this CLIC team. I'm delighted to participate in this official launch. Zoe and Annabelle asked me to share for 10 minutes on the learning sciences and how it relates to the science of learning. My perspectives are probably not mainstream to most of your understandings, but since I'm asked to share, let me give my take on this issue. The title of this short presentation is Science of Learning and Education, a Bilateral Perspective. I would caveat that the science of learning which I refer to is the more applied side of science of learning more generally, not the biological aspects of cell biology, which is a bridge too far, in my opinion, to education. An example of applied SOL work is working memory. Instead of seeing neuroscience primarily as a translational pathway to learning and education, that is T1 to T4 in a linear fashion, I would like to propose that education can be a pathway to neuroscience in the reverse order, at least metaphorically. I will elaborate this subsequently. I argue that insufficient emphasis is placed on the problems of practice. This is consistent to Pasteur's quadrant, the use-inspired research driven to solve practical problems. At the NIE, I hope to draw synergistic and interdisciplinary links between science of learning and education so that research investments for health and human potential, HHP in short, can be worth the while for the school system in Singapore. At least this is my understanding from my colleagues at MIT. In the past 2 decades of education research, we have already understood many workable in practice learning interventions with ecological validity. But we might not understand why some of these interventions do not yet work for certain specific sub-cohorts, example, low progress students. And many of these projects can be classified by lifelong, life-wide, life-deep, and life-wise perspectives. The learning sciences, which is not the science of learning as we know it today, focuses on social cultural aspects of learning, that is, how the environment interacts with cognition. Cognition is seen both individually and collaboratively. It is not the individual or the environment per se, but the intersection or interaction between the two, which is the focus of learning sciences research. On the other hand, experimental studies have given us insights into how learning occurs with specificity towards certain individual cognitive processes such as executive functioning, but they would not also need to be situated in schools and classrooms for it to have impact, where there is a myriad of individual and environmental factors that exist there. That is, if experimental design researchers desire to make impact to education in schools, the end goal is important to be kept in the minds of researchers. The learning sciences research studies focus on interactional or mediational mechanisms that can enhance domain-specific conceptual understandings in inquiry through the use of multiple representations, linguistic scaffolds to guide disciplinary thinking within stipulated zones of proximal development, the social construction of meaning-making such as in teams and in collaboration efforts, and identity formation as a critical tenet in simulated communities of practice, simulating the communities of practice in disciplinary contexts where you and I typically exist in. And there are many other learning principles of which I've just listed a few. However, while various design-based interventions used by the learning sciences are situated within classrooms, the impact trajectories of our interventions at scale is still weak. Some nascent efforts have been put in this front on work relating to school and teacher leadership and also system structures. There are mechanisms for scaling and sustainability. Policy is inevitable when we hope to bring interventions to the system scale level of analysis. The example shown here is one where school and cluster level mechanisms were deployed with the support of heads of departments and school leaders, with the sharing of teacher domain expertise across the cluster of schools in science inquiry and in the use of technology. What is critical from the teachers' enactment's point of view is the collaborative group of teachers working across schools to figure out the task designs needed for inquiry as they engage in science inquiry for their students, the facilitation of dialogue and classroom routines, and the so-called new culture of inquiry learning that would arise in such a context. This is to the extent where learning sciences and educational researchers play a role. In my humble view, when we start with experimental designs in controlled environments, and for good reasons to do so, we need a way to better ensure that many of our T1, T2 studies lead to T3 or T4 outcomes, where use-inspired applications, in this case, classrooms and schools, find efficacy in the kinds of interventions proposed. Since we already know many workable interventions in classrooms, we can, in a reverse fashion, start at T4, understanding what has worked and what did not, and seek experimental designs for answers to that which did not work. This is what I mean by starting with problems of practice. I suppose the frontier that we can still explore in the science of learning is to understand and identify leverages for human potential of students, where opportunities along the schooling trajectory permits where students' human capacities can still be leveled up where it was previously unexplored. For example, in exercise, sleep, and diet, and so on and so forth. These are the so-called non-traditional individual factors as seen from the lens of educational research. Let me take deep breathing as an example of how SOL and education researchers might work together. SOL researchers might propose the intervention of deep breathing, decontextualized, as a way to reduce the stress experienced by some less regulated students. The intervention might not be situated in schools or classrooms per se, but advises on deep breathing exercises as a training program. What we are suggesting is that we cannot assume that these decontextualized interventions can sustain even if they work and are proven with data to support it. We need a lot more efforts in contextualizing these interventions in regular classrooms and in classroom curricular-based activities such as physical education. From the reverse process, that is education to neuroscience, we can begin to study how deep breathing occurs in established physical education curriculum, such as in swimming. I heard in BBC a program that swimming reduces anxiety. Now, assume we can put physiological sensors on students, and as they enter into the pool and swim, we monitor their deep breathing. Now, if we are able to take this data and compare that with the experimental designs we had earlier, we might be able to find a middle ground through which both kinds of research approaches inform practitioners how to enable deep breathing among our students. Recognizing the two apparent opposing paradigms and their different assumptions, we can rise above and see as complementary the evidences collected and use the data generated to practically and pragmatically co-inform each other, and not see one as superior against the other. This is where interdisciplinary efforts weigh in. Interdisciplinary R&D is probably easier said than done. If you can allow me, the current focus of MOE on low progress students is one potential interdisciplinary area of R&D that can bring different fields of study together. R&D trajectories in low progress students require both science of learning and education policy solutions in order to develop interventions that sustain across time, capitalizing on understandings where the leverage points in the students' school trajectories are, and on policies that enable multiple partners in the community, such as social service agencies, to work together for the betterment of the students and their families. Science of learning techniques can be applied to understanding the neural correlates of low progress students and their particular cognitive abilities, for example, in literacy and numeracy. And social education policy and its mechanisms can deal with the issues of teacher professional development, sustainability, and scale. However, they need not be treated in a T1 to T4 staged linear fashion. The recent scientific developments in COVID-19 vaccines developed at lightning speed is one example where parallel dialogue between the evidences collected insofar as COVID-19 vaccines are concerned and the policy rollout of vaccines to rich and poor countries alike need to work hand in hand. The recent events are unprecedented and show us how important interdisciplinary research and dialogues are crucial at multiple levels of analysis and implementation. In this interdisciplinary vein, the University of Cambridge and NTU proposed CLIC. Cambridge and NTU researchers have complementary expertise in the neuroscience of learning across the lifespan. Importantly, NTU and NIE researchers have the local knowledge necessary to contextualize the approach proposed in the study within the Singapore's education system of schools and classrooms. For the CLIC project to CLIC, the team can do more to partner key stakeholders, in particular the Ministry of Education and adult learning agencies, with regular dialogues and updates to make its findings impactful and able to find traction with policymakers and contextualize to school routines and practices early on in the research cycle. SOL and education can make headways with good returns to HHP investments if we attend to grand challenges such as leveling up low progress students, and we work out mechanisms for how research evidence travels to where the problems of practice exist, influencing key stakeholders that matter in the process. Finally, let me sum up. If we use SOL techniques to improve HHP gains in individual factors, those beyond the purview of educational research traditionally speaking. Number two, adopt learning sciences approaches, leveraging on the context and learner mediating mechanisms, delving into those that are more efficacious compared to others for different groups of students. And number three, work with social education policy researchers and practitioners to identify leverages as an education system and build towards an ecology of partners with a view to sustaining interventions and scaling up. I think we will make good progress and good commitments for impact to the education system and beyond. To do the above, I reckon that we need bilateral conversations between the science of learning and education. Thank you very much.
Thank you very much, Professor Hang.